This is my third lecture about overviews of entire chapters from this book, The Mathematics of Investment and Credit, for my class, Financial Math for Actuarial Science. And this one's about loans and loan repayment. And again, what I focus on are the main mathematical aspects of things. There are lots of practical aspects of things, for example, laws related to loans and lending in general, that you'll find in the textbook and you should read about it. Again, I focus on the math. And like I did in lecture 2, I want to start by doing some loose ends from the preceding lecture. So we'll start just by talking a little bit about annuities, and in particular continuous annuities. So this is loose ends from the end of lecture 2. Let's consider the simple situation of a level continuously paid annuity. So we're paying it at a certain rate, a certain constant rate per unit of time. H of t is that constant rate per unit of time, 1 unit of money per unit of time. We've got a constant force of interest, delta sub t is a constant delta, which is natural log of 1 plus I, where I is the effective periodic interest rate, over the interval from time 0 to time n, and oftentimes n is an integer. But it doesn't have to be. Present value you find by doing an integral. This is the same thing as v to the t, where v is the discount factor. But of course, with integration, it's more handy to have it in terms of e. Integrate e to the negative delta t. You should check this on your own, that you get this simplified formula for the present value of this income stream, or this payment stream. And you should be able to think about such an equation qualitatively, and you should be interested in thinking about such an equation qualitatively. What do I mean by that? I mean in terms of graphs and their interpretation. I've got a Mathematica notebook here, where we can take a look at graphs related to this equation here. What I'm first going to graph here is this present value as a function of delta, the interest, the force of interest. And I can let n change and see what happens to the graph as n changes. So here n is set to 1. And you see it looks like the present value with one payment is constant in terms of delta. The value of delta doesn't affect it. However, as n increases, you see a graph that definitely is not constant. It's definitely decreasing and concave up, like this. And it should make sense here. You see that n, the number of periods here, is 14. As delta goes to 0, as the force of interest goes to 0, which is equivalent to the interest rate itself, I going to 0, the present value is approaching 14, which is going to be the total amount of the payments. So if you integrate the constant function 1 from 0 to 14, you get the area under the curve, which is a rectangle, which would be 14. When you have no interest going on, the present value is the same as the total value that you get in the end. As the force of interest, the interest rate goes up, the present value goes down. What does that mean? It means that it's worth less right now at the beginning if you've got a high rate of interest, because you could deposit, for example, at a 10% force of interest, a smaller amount, about 9, and get the same future value. It would be an equivalent thing at time n as this entire payment stream, because interest is higher there. You can gain more interest over time. So the present value is smaller. You can use Mathematica to confirm the limit of this function as delta goes to 0 equals n. 14 was the case that we looked at. You can also verify this limit with L'Hopital's rule, thinking of it as a function of delta, differentiate the top and the bottom as functions of delta and take the limit of the resulting thing. You can also plot this as a function of n. And I guess I am thinking of n as being a whole number here. I guess I didn't really have to. Again, we are plotting the present value, but now as a function of n for different fixed deltas. When delta is 0.001, 1/10 of 1%, the graph looks like this. What happens as n increases, or as delta increases? The graph still increases, but is more clearly concave down in shape. Certainly as the number of payment periods, the entire interval of time you're talking about, goes up, the total present value should go up. When, again, the force of interest is close to 0, the value at the given value then, 25 in this case, the present value is very close to 25. It's very close to the value of n because we don't have much interest going on there. It does appear that as delta gets larger, perhaps this graph has a horizontal asymptote. Just looking at a picture like this is not enough to prove that. But you could calculate this limit as n goes to infinity to confirm that. You can, of course, do it in your mind as well. As n goes to infinity, since delta is positive, this thing goes to 0. The limit of this, as n goes to infinity, should be 1 over delta. Mathematica confirms that. Delta, you can see in this particular situation, is 0.1. 1 over delta would be 10. You can see the present value is approaching a value of 10. That would be a horizontal asymptote for this graph. What about an increasing continuously paid annuity? H of t equals t. Over the interval from 0 to n. Once again, the present value this time is symbolized by I bar A bar sub n. It's this integral, which is, of course, a bit trickier to do, but you should, as an exercise, do this integral on your own, confirm this equation. You'd want to use integration by parts, let u equal t, and let dv equal to e to the negative delta t dt. Use the integration by parts formula and confirm this. You could also confirm the equality of these two things by substituting what was in the last slide in place of a bar and doing some algebra to see that these things are the same. But once again, you should be able to and interested in thinking about such an equation qualitatively in terms of graphs and their interpretation. I could make similar kinds of graphs, and in fact I did. And in fact, in this particular animation, I can compare both the graphs of A bar and I bar A bar. That's what I plan to do at least. Let's see, I gotta enter this. That's the problem. There we go. So for a given value of n, A bar is the red graph and I bar A bar is the blue graph. You see this little funny thing going on here? That's just computer error. With real small values of delta, you get some numerical error. The graphs really do look like the main parts that you see. And in both cases, again, the graphs are decreasing and concave up. The fact that they're decreasing means that when the interest rate is high, you don't need as much money initially. The income stream, so to speak, is not worth as much initially as in terms of its present value, because you could take that chunk of money and deposit it somewhere else for that high interest rate and still get the same future value. Does the blue graph has a limit as delta goes to 0? Yes, it does. And that limit is n squared over 2. Why would it be n squared over 2? Why don't we come over to the board here? H of t is t here. If the interest rate is 0, the present value of this thing is going to be the same as the area under the curve. We don't have to discount this function at all. And the area under the curve there is going to be 1/2 n times n, 1/2 n squared. 1/2 base times height, it will be a triangle. And therefore, that's why this limit is n squared over 2 coming back over here. Once again, you can make a discrete plot if you want to think of n as an integer. And it looks like that blue graph, this present value, looks like it's concave up forever, perhaps. But actually, that's deceiving. If you make the interest rate higher, you see that the graph actually does become concave down at a certain point. And actually does have a horizontal asymptote. Okay, of course, in both of these situations, as n increases, the present value is going to increase because you have more payment over time, a bigger interval of time. But there is a horizontal asymptote even to the blue graph. As n goes to infinity, the limiting value of I bar A bar, really, is 1 over delta squared. Okay. Technology can help you deal with oddball examples, technology like Mathematica. We could take our force of interest to not be constant. We could take it to be this periodic function. We could take our h of t to be not constant, or even a simple increasing function. We could take it to be this periodic function. And while this would be difficult to do by hand and analyze by hand, you can write equations involving integrals for example, the future value. I could also do the present value. All right? And in the next slide, I'm about to show you the graph of this thing as a function of n, thinking of n as a continuous variable, which you can do in this context. These equations, by the way, were in lecture 2, and if you're confused about where they come from, you should probably watch that lecture. In the very end of that lecture, I do talk about these equations a bit. And again, thinking of this thing ultimately as a function of n, here's the way its graph looks like, and it's kind of interesting. It is an increasing function, but it wobbles, okay? Sometimes concave up, sometimes concave down, which maybe shouldn't be surprising since those other functions for delta, sub t, and h of t were trigonometric periodic functions. So that's kind of interesting. You could use the computer to also estimate the value of this at any particular value n. Is this realistic? Would such oddball examples occur in real life? Well, probably not perfectly, but maybe it's not too far off. It's conceivable the interest rate could oscillate in a somewhat periodic way. And it's conceivable your cash flow could oscillate as well. For example, if you're a big multinational corporation, and you're getting money, and you have good seasons like, say, Christmas time, and drier seasons, say, like maybe February or March, your income that you get, your revenue, could vary in sort of an oscillatory way. I'm sure it wouldn't be exactly these kinds of formulas, and if it was this kind of formula, it would have to be like in billions of dollars per year or something. That would have to be the units, but it's conceivable this wouldn't necessarily be too far off from something that could be realistic. All right, now we're into chapter 3. We're into loans, our main content for this lecture. It's a bunch of loan terminology, symbolism, and basic equations you want to get down. And this is going to be pretty equation heavy here, as many of these subjects are. But we might, in lecture 4, think about these things qualitatively too. And you should try to think about these things qualitatively. Another thing you should think about when you see these kinds of equations is you shouldn't worry too much about deriving them algebraically. Of course, that is important to be able to do that. But it's more important, especially in the context of taking exams, that you understand these things intuitively. So that in case you have forgotten them, if you're focused on memorizing for actuarial exams, you could sort of rethink about what they would be. They make enough sense to you that you could sort of rederive them. So we've got a loan amount. What is a loan? Okay, a loan is where somebody's borrowing money, or some company's borrowing money from somebody else, or some other company, some bank, or even the government. You're borrowing money and you want to pay it back with interest. So the L is the symbol we're going to use for the loan amount. It's a certain amount of money, and we've got a certain periodic interest rate that is part of the term of the part of the description of the loan, I, and a corresponding discount factor B to be the reciprocal of 1 plus I. That's 1 plus I to the negative 1 power. We have n payments, and to keep it simple, we assume these n payments occur at times 1, 2, 3 through n. Theoretically, they could occur at varying times that are not equally spaced, where the amount of time does correspond to the periodic interest rate. So if I is an annual interest rate, these times would be years. If I is a monthly interest rate, these times would be months. If I is a daily interest rate, these times would be days. These are nominal amounts, because we haven't discounted them, K1 through Kn. What's this funny thing? That's the problem of trying to go from a Mac to a PC. This is supposed to be a dot, 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 and I didn't realize this would happen until just now. Okay, K1, K2, K3, dot, 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 Kn are our payments. And for a standard loan, the present value of these payments must equal the loan amount. Okay, the standard loan, pretty much any loan, this is going to be the case. There would only be some sort of strange thing where maybe the lender is trying to fool you, where this wouldn't be the case. Think about a timeline here. Come over to the board here. Payment K1 has to be discounted back to time 0, so I need to multiply K1 by V. K2 has to be discounted back 2 periods to time 0, so I need to multiply by V squared. K3 needs to get multiplied by V cubed, because it goes back in time by 3 periods, and that's where you get this equation that you see. L has to equal that thing. Typically, the payments are level. K1 through Kn equal some value K, and therefore, you can factor out the K out of this equation and get k times the sum v plus v squared plus dot 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 plus v to the n, which is the present value of an annuity immediate. And we use this symbol for that present value. That's what I talked about in Chapter 2, Lecture 2. And then you can solve for your payment. K will be the loan amount divided by that present value of a, again, this is for an annuity immediate with payments of 1 over n periods with interest rate I. So this equation is pretty fundamental. You can use it to find how much you need to pay for the loan per period. What's some other fundamental equations? In symbols, in terms, OB sub t stands for the outstanding balance at time t. And for a typical discrete kind of loan, you will have a value OB0, which stands for the initial loan amount. You'd have a value OB1, which stands for the balance right after the first payment. Then you'd have an OB2 that stands for the balance right after the second payment. Just after payment T is made, and OB0 is taken to be L. If we're paying with a continuous payment stream, then T would be a continuous variable, and we will talk about that at the end of the lecture. IT is the interest that you pay on the outstanding balance since the previous payment was made. Interest that is accruing from time T minus 1 to time T. It's the interest on OB sub T minus 1. So for example, I1 is the interest on OB0, and it would be found by taking that value, OB0, times the interest rate, the periodic interest rate, which is often a monthly interest rate. And that gives you I1. I2 would be OB1 times I. PRT, what does PR stands for? PR stands for principal reduction. Your principal, the amount you owe, is going down over time. How much does the outstanding balance go down? It's the portion of payment KT that goes toward reducing the principal, reducing the value of OBT minus 1 to a new lower value, typically OB sub T. And here are some equations that should make sense. And again, I really, really want to emphasize these are not things to memorize so much as to look at and say these make sense. The interest on payment T plus 1 is going to be the previous balance, outstanding balance at time T, times the periodic interest rate. Again, often it's a monthly interest rate. Often the payments are monthly. Principal reduction at time T plus 1 is the payment, total payment at time T plus 1 minus the amount that goes to interest. Typically, K is bigger than I, so typically this is a positive quantity, but there actually are some situations where K is not bigger than I, and this could be a negative quantity. And your balance then would actually go up over time. Okay, that can be simplified by using this equation to what you see on the right there. Come back over here, OBT plus 1, the balance at time T plus 1 is the preceding balance minus how much the principal gets reduced, and if, again, you're subtracting a positive number there, typically, this will be smaller than this. If the principal really is not reduced and this is a negative number, then OBT plus 1 would be bigger than OBT. That happens sometimes, but it's not typical. You can replace the PR with this difference, like that, and you can rearrange, put the OBT terms together and factor out the OB to get a 1 plus I. And this equation should make sense too. You take the preceding balance, put that forward in time by 1 period by multiplying it by the promotion factor 1 plus I, and then subtract out the next payment to get the new balance at time T plus 1. All these things, again, should not really be memorized. They should be looked at and say, those make so much sense to me that I could rewrite them down anytime I want. Or I could, maybe I don't rewrite them down with symbols, maybe I just rewrite them down with numbers. This all leads to something called an amortization schedule, which is a big table of values of times, payments, interest amounts, principals repaid, and outstanding balances. We're going to look at something called a spreadsheet here in a minute where we do this kind of thing, but basically you have a big grid, and I'm only showing you part of the grid, one row in the grid, at time T plus 1. Payment is called K sub T plus 1. The interest due is I sub T plus 1, which equals this product. The principal that's repaid during that, at that moment in time, T plus 1, is this. And the new balance right after that principal is repaid is the old balance minus the principal amount that was repaid there. The preceding balance minus the principal reduction at time T plus 1. Let's go ahead and go to a spreadsheet now. You know, you're not going to be able to use a spreadsheet on actuarial exams, but every actuary should know how to use a spreadsheet. Here's an Excel spreadsheet. I often use Google Docs as well. Google Docs spreadsheets works pretty much the same way as Excel. There are a few minor differences. So what do I have here? Zoom in on this as I talk about it here so we can see it okay. We've got a certain loan amount. I took it to be $20,000, which you could think of as being a car loan, for example. We've got a nominal interest rate, annual interest rate, convertible monthly, meaning compounded monthly. I took 10% there. You've got a monthly interest rate, which is the nominal annual rate divided by 12. If you take 10 and divide it by 12, you get 0.83 repeating. 3's repeat. And I'm taking the number of months, in this case, the term of the loan in months, to be 36, which is the same as 3 years, which is a common kind of car loan. Down over here to the right, you see the start of this amortization schedule. I've got the time, the payment KT, which is going to be constant actually, the interest IT, the principal repaid PRT, and the outstanding balance OBT. Before I fill in the schedule, I've got to figure out what the monthly payment is. Let me first think about this in terms of the formula that I showed you a few minutes ago. When you have when you desire a level payment to your loan, which is the typical thing, that payment amount, KT, is a constant K, and it was the loan amount divided by the present value of a standard annuity immediate with payments of 1. Let's go ahead and apply this formula here, where AN is 1 minus V to the N over I. I'm going to go ahead and use spreadsheet's formula capabilities, which is something you're going to want to learn how to do, to figure out what this present value is, and ultimately figure out the monthly payment by doing that division. I'm also going to show you a built-in function in the spreadsheet called PMT that can calculate this monthly payment without doing this calculation over here. Well, let's go ahead and do this calculation. Let's first figure out AN. So what I'm doing here, look at the screen again, is I'm going to do 1 minus V to the N. What is V? V would be the monthly discount factor, which would be 1 plus this thing as a decimal, 1 plus 0.00833, to the negative 1 power. That would be what V is. When I raise V ultimately to the 36 power, I can raise 1 plus this thing to the negative 36 power. Now that interest rate is in cell B3, and instead of typing 0.008333, I'm going to type the cell reference. This number is in cell B3. It's good to do it with the cell reference because that can allow you to make changes, and those changes get updated appropriately. I need to raise this to the negative 36 power. 36 is in cell B4. Use a B4 because that could change as well. You might want to change the term from 36 months to 60 months, for example. And I need to divide this by I. I is, again, in cell B3. So this should calculate AN. Okay? There's 36 payments of 1 for AN. We're taking a present value, so this value should be less than 36. I'm not sure how much less than 36. That much less, about 31. What's the monthly payment then? Take the loan amount, which is in cell B1. You can also just click on the cells to get the cell reference, and divide by B5 here. The monthly payment is going to be that ratio in dollars, $645.34. But yes, I can make changes. And by the way, I did in cell B3 type of formula in that as well. I took equals B2 divided by 12. So I took the annual nominal interest rate and divided by 12 to get the effective monthly interest rate. I could change that nominal annual interest rate to, say, being 5%, which I think I have to type as a 0.05, though it's going to display it as 5% based on the formatting. This now becomes 5 divided by 12 is that, approximately, and the monthly payment went down. Yeah, there is a built-in function in Excel and other kinds of spreadsheets, typically called PMT, that can calculate monthly payments for you without using this formula, without bothering to find this present value. You see the syntax for this function first involves plugging in the periodic rate, which is going to be in cell B3, comma, the number of periods, zoom in on that if it's small, n per means n, number of periods, that's going to be in cell B4. Present value is the loan amount, though there's a convention here because you're thinking of this loan amount as being a negative thing to you, you're paying this money out, you actually need to make this a negative quantity. The future value is going to be 0 because we pay off the loan by time n, and the type is going to be 0 for an annuity immediate. These payments are at the end of the periods. It would be a 1 for annuity due. So I'll put the rate in, cell B3, it's the monthly rate, number of periods, 36. Present value, put a negative sign, negative sign B1. Future value 0, type 0 for annuity immediate. And then you see these two numbers match. Okay? So it's good to see that. Now let's fill in this amortization table. We're doing it for 36 months. Let's put month 0 here. Time 0 is when you take out the loan. I want the times to go up by 1. I can do a little trick. I can do B equals B8 plus 1. I can type it here. B9 plus 1, excuse me. Take the preceding cell right above it and add 1, and I can copy and paste that formula downward, which is good. It will get updated correctly to being equals B10 plus 1 in this cell, equals B11 plus 1 in this cell, and therefore these numbers will be 1, 2, 3, 4, 5, 6, etc., and I want to go down to 36. You can either copy and paste those things, or you can click and drag the lower right corner of the cell. And I think I got to go to line 45 to get to 36 months here. Yes, there we have it. 36 is the last month that we see. For this time 0 line, only fill in the outstanding balance, which is the loan amount, which is in cell B1. So I'm pulling the loan amount over to this cell. That's outstanding balance at time 0. The payment I get from cell either B6 or C6, and I want that to stay fixed as I copy and paste downward. I don't want it to get updated to being B7 and B8 and B9 because those aren't the loan amounts. The loan amount there is in B6. The trick for making that cell reference stay fixed, at least its row, is to put $1 in front of the 6 in B6. However, I'm just going to default by putting $sign in front of the B as well, to fix the column as well. It's not really necessary since I'm going to only be copying and pasting in this column. But typically that's what I just to sort of play it safe, I put $sign in front of the B and in front of the 6, in front of the letter and in front of the number. That keeps the cell reference fixed, and as you paste it downward, it doesn't change. It'll stay a B6, which is what you want for these level payments. So there it is. The interest rate, the amount of interest for this first payment is the outstanding balance from the previous line, F9, times the interest rate, the monthly interest rate, which is in cell B3, and I want that to stay fixed as I copy and paste downward. So I use $signs on that one, $B, $3. So this interest on this initial balance is essentially going to be 1/2 of 1% of this balance. 1% of this is 200. So 1/2 of 1% is 100. This is going to be a bit less than 100. It's going to be 80 something, it looks like, of interest in your first payment, 83.33. Don't worry about the extra decimal here. How much goes toward reducing the principal? Principal repaid. Take the payment, C10, and subtract how much goes to interest, D10. That difference, which is going to be around 516 or so, will be how much your principal gets reduced after that very first payment. And I want those cell references to change, so I did not use $signs. Now take the previous outstanding balance in cell F9 and subtract how much the principal gets reduced in cell E10. No dollar signs there. I want that to get updated to being F10 minus E11, etc. I think now we are ready to copy and paste this row all the way down. And what should happen is at time 36, the outstanding balance at time 36 after the last payment should be very close to 0, if not 0. It might be slightly different than 0 from rounding issues, but I think probably the spreadsheet keeps the internal decimal expansions more than what you see here. There we go, and in fact, yes, it is coming out to be exactly 0 at the end. Actually, in real life, sometimes it can be definitely off by a few cents, and in the very last payment, you might need to add a few cents or subtract a few cents even from your last payment. But the bank will usually tell you that. But here, because it's keeping more decimals, it comes out to being 0. These dollars and cents amounts are essentially approximations that wouldn't necessarily match exactly what happens with what you do in your payments. So this comes out to be exactly 0 by time 36. We have paid off the loan. And you could find things like how much total interest did I pay? I could add up column D, D10 through D45, for example. I could use a built-in function equals sum, D10 colon D45, to add up all those interest amounts to get the total amount of interest I pay over the life of the loan. $1,579 here in this case. I could also figure that out by figuring out the total payments, add up all these numbers, minus the original loan amount should be the same thing. The total payments would be equals sum C10 through C45, and as I subtract 20,000 from this amount, I get exactly this amount, the total amount of interest paid. Okay, so those kinds of things should make sense. It's also a good idea to graph, for example, the outstanding balance as a function of time. I can highlight the time column, and on a PC, I think I hit the control button. On a Mac, you hit the command button. I'm holding it down, and I'm also highlighting the outstanding balance. And I want to go up to Insert, Chart, and I could use the line chart. I think I'm going to do a scatter plot that's connected like this. And there you do see the loan balance going down as a function of time. It's definitely decreasing, and it is slightly concave down is what is typical. If I take this chart and make it go up higher here so I could see it with the initial amounts here, I can now make changes to these things and see how the graph changes. For example, I could make the interest rate really high, like 20%. Ready? Everything's going to change. Watch this. The monthly payment's going to go way up too, to $743. And yeah, the graph changed, and it became more clearly concave down now. And when you have high interest rates, that's what happens, is you get clearly concave down kind of graph here. That also happens if n is very large. For example, with a home mortgage, which is 30 years or 360 months, you definitely see a strong concave down nature to the graph, indicating that at first, a lot of your money is going toward interest and not as much toward principal reduction, but later, a lot of it's going toward principal reduction and not as much toward interest. All really important things to know from a practical perspective as well here. All right, we continue on here. Let's go to the next page. More formulas, okay? And again, I re-emphasize you should know these formulas intuitively. That's probably more important than being able to verify them algebraically, though algebra is still good. These formulas are actually pretty simple. They should make good sense. Total payments minus total interest paid equals the loan amount. K total minus I total does equal L. Okay, and you can algebraically verify it like that. This could be thought of as a sum of all the payments. This could be thought of as a sum of all the interest payments. By properties of summation, you can combine those, and those are your individual principal reductions at your various times, and that simplifies to the loan amount. You can also say the total interest paid equals the sum of the interest amounts paid on each outstanding balance. And maybe that's a little less obvious, but it's algebraically verifiable. The total interest is the sum of each individual interest which can always be thought of as the preceding outstanding balance times the periodic interest rate, and I can be factored out of that summation to write it like this. I also change the index, the way the index goes, because OB0 is the first outstanding balance. But these mean the same thing. And this is telling you your total interest is I times the sum of the individual outstanding balances, which could be a useful thing in some problem-solving things. The next few slides I'm going to show you are probably the most important in terms of problem-solving for Actuarial Exam 2 on financial math. There's formulas for finding the outstanding balance at an arbitrary moment in time. There's something called the retrospective method and there's something called the prospective method. They give you two seemingly different formulas, but they do give you the same value. To derive the retrospective method, you can write a sequence of equations for individual outstanding balances, and I could have written it for OB4 as well, but I ran out of room. And what you're looking for is a pattern, okay? And it's just algebra going on here. OB1, the outstanding balance at time 1, is the original balance, the loan amount, promoted in time by 1 period by multiplying by 1 plus I. Subtract the payment at time 1, that'll be your outstanding balance at time 1, right after that payment. Same kind of thing for outstanding balance at time 2, and because of the preceding equation, we can substitute that in place of the OB1 and do some algebra to rewrite that like this. Same kind of thing with OB3, and ultimately we can write OB3 as the original loan amount promoted in time by 3 periods by multiplying by 1 plus I cubed and subtracting the promoted values, the accumulated values of the first 3 payments here, and that should be an M there, typo right there. You want to zoom in on that? This should be an M, and I didn't want to use an N for the index of summation because N typically stands for the number of periods. So this should be an M right here. These M's are correct. Then you can check out that that formula does work. And in general, and here I used an M correctly, you can have this form of the outstanding balance at time t. This is called the retrospective form of OBT. You're thinking backwards in time. The word retrospective comes from the fact that you're thinking about amounts on your timeline that are backward in time from time t. Your original loan amount, OB0 or L, promoted in time to time t by multiplying by 1 plus I to the t. T is a positive integer here. And then you're subtracting off the promoted values of the payments. You've got an arbitrary payment here at time m, km. It needs to get promoted in time to time t, so that's t minus m periods. So I need to multiply km by 1 plus I to the t minus m to get that promoted value. I'm doing that for all the k's from 1 to t. When m equals t, you really get t minus t here, or 0 power. You get a 1 there. Kt is the time t payment. The balance is the difference of these two things. Promoted value of the loan amount minus the promoted values of all the payments. Again, it's called retrospective because you're looking at backward in time, though you are pushing them forward to time t. There's something called a prospective method as well, where you are now looking forward in time instead of backward in time, and you are discounting values back to time t instead of promoting them. You can take the retrospective method and replace OB0 by L, and also replace L, I didn't have to use the L, by the present values of all the payments. That was the equation we saw, oh, I don't know, 20 minutes ago or so. And through various kinds of algebra, you can derive this equation here. I'll let you look this over and double check that things seem right. I believe there's no mistakes here. I did double check this all before. I believe I did not find any mistakes. Do keep in mind, of course, that 1 plus I is the same as v to the negative 1. So, for example, when I multiply these two things, this is really the same as v to the negative t. So I get v to the m minus t, or equivalently 1 plus I to the t minus m. Same as v to the m minus t. But it should make sense intuitively. You're at time t. You're taking the payments starting at time t plus 1 and going to time n. and you are discounting them backward in time. kt plus 1 goes back by 1 period, kn goes back by n minus t periods. Kn goes back by n minus t periods, you can see. It's called the prospective method because you are thinking about payments that are to come forward in time, and you're pulling them back to the present, discounting them to time t. That's called the prospective form. And they give you the same value. The retrospective and prospective methods have to give you the same value. It is the same. They are equivalent to each other. All right, you hanging on here? How are we doing in time? I should probably look here. Another 15, 20 minutes. In the case of level payments, where all the k's are the same, you can simplify these formulas. You can simplify the retrospective formula to being, for example, this, where S is the future value of a standard annuity immediate with payments of 1. K is the amount of the individual payments. L is the loan amount. We are talking about time t. That can be written this way as well. The prospective method can be written this way in terms of the present value of an annuity immediate with payments of 1. And in both of these cases, K, the payment per period, is equal to this. We talked about that equation again around 25 minutes ago. That can also be written if you replace an with 1 minus v to the n over I and take its reciprocal. Since you're dividing by it, it can be written this way. That's the amount of your payments in this situation. Okay, so those are simplified formulas that you could use when the payment level is constant. There's other relationships worth knowing for the level payment case. Here are some other equations worth knowing. When you have a level payment of K at the end of n periods on the loan L with periodic interest rate I. Again, not that you should necessarily memorize all the equations I'm about to show you, but they should make good intuitive sense to you. That's the more important thing, because if you don't have them memorized, you can figure them out. They just make sense to you as you're taking the exam. The total amount of payment that you pay is, well, very logically, the number of payments times the payment amount. Of course, that's going to be bigger than the loan amount typically, unless your interest rate were negative, which it never is. Okay? You can write IT plus 1, the interest paid at payment T plus 1, as the interest rate times the previous balance. You can replace that previous balance, thinking prospectively with this symbolism. You can replace A sub n minus t with 1 minus v to the n minus t over I, and cancel the i's to write it this way. Okay, that's worth knowing right there. That is the amount of interest on payment T plus 1. That might be a little harder to think about intuitively, but this is a pretty quick derivation. How about the total amount of interest you pay? You would add up things like this. That's what I've got. Adding up things like that. And, well, you have n k's, if you use the distributive property here. So I get n times k, which is what I also have down here. And I also have k, minus k times, in parentheses, v to the nth plus v to the n minus 1 plus dot 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 plus v, which is going to be an, which of course you can also write this way. And this says something very intuitive. The total amount of interest you pay is the total amount of all your payments minus the original loan. We saw that in the spreadsheet. You can solve this last equation for L. The loan amount is the total amount of all your payments minus the total amount of all your interest. And you can also figure out simplified formulas for the principal reduction at time t plus 1. Essentially, if you, for example, set the total interest, think of the total interest or at time t plus 1 as being, what would it be? It would be the interest plus PR would be K. So I would be K minus PR. You can derive this equation for PR, the principal reduction, which can be written in a couple different equivalent ways. Notice you can write it in terms of promoted values of the first principal reduction. So what this is showing is your principal reduction values grow geometrically. You need to keep multiplying by factors of 1 plus I to get the next principal reduction amount. That's worth knowing too. Here's a different kind of situation. Okay, so what I've all done so far is just standard situations where the total payment per period is constant. Theoretically, you could have other kinds of payback schemes. Another, maybe the second most common, I don't quote me on that, maybe it's the third most common, is where your payments to principal are level. Your total payment goes down, your payments to interest go down, but how much of each payment going toward reducing the principal stays constant. You got a loan L paid back with n equally spaced payments where the amount going toward reducing the principal is constant at L over n per payment. The amount of interest on each payment is the previous outstanding balance times the periodic interest rate, as always. What this means is PRT is constant. OBT is a linear function of T. The graph of OBT, if you think of it as discrete here, is going to be points that are on a straight line, and I'm not drawing that very well, going down. That'll be OBT as a function of time, a linear decreasing function of T. The amount that goes toward interest is also a linear decreasing function of T. By the way, when you look at these equations, they are probably something you wouldn't memorize, but you should be able to derive pretty quickly. They should make good sense to you. And you see this interest in the Tth payment is also a linear decreasing function of T. I believe there are no typos here. I could look this over, hopefully. I double check things. Here is the amount of each payment, also a linear decreasing function of T. This is not a level payment total. It's a linear decreasing function of T. KT is going to look like that. It doesn't go down to 0, it goes down to some final amount Kn. When T is n minus T is 0, I get I plus 1 times L over n for the final payment amount, which is not 0. And what else can you say? You can say your total interest is given by this amount. I'm not going to go through the derivation here. This is something you should be able to verify. I will tell you that in this derivation I used a formula that not everybody knows, but really every actuary should know. And that is if you add up the first n integers, you get n times n plus 1 over 2. Mathematician, the story is a mathematician named Gauss knew this formula pretty intuitively when he was like 3. And I don't know, he was in preschool or something, 4 or 5 years old, and the teacher had the students add up the first 100 numbers, which is a pretty quick derivation of this involving switching around the order of the numbers and then adding the two equations. And Gauss did that like as, you know, a 4 or 5-year-old in his head just like that and produced the answer on his slate. And he didn't have any more punishment because of that. For example, when n is 100, you get 100 times 101 over 2, which would be the same as 101 times 50, which would be 5,050 is the sum of the first 100 numbers. That is a formula that I used in going from this step to this step right there. And I'll let you see if you can derive that. But then this might be worth memorizing here, this last one. That might be something worth memorizing for actuarial exams, but certainly if you get enough practice at this, you could rederive it pretty quickly if you know this formula up there. Another kind of payback method involves something called a sinking fund. Sometimes a borrower only pays interest on each payment until the very last payment when they pay interest plus something called a balloon payment, which is a very large payment which also pays off the loan. Okay, so for every payment but the last, they pay L times I, where I is the periodic interest rate, often a monthly interest rate. And then the last payment, payment number N, they pay LI plus L. How do they raise money for that final huge payment? They invest in another account, something called a sinking fund. They invest at some periodic interest rate J, which often is less than I, which to me doesn't make sense. Why would you do it this way unless you get J to be bigger than I, so you come out ahead in the end. But often you can't find an interest rate bigger, so I don't know. Maybe you just don't have enough cash right away and you're hoping besides your investment in the sinking fund you can invest in maybe your company and raise enough money to pay off the final balloon payment. You invest at periodic interest rate J at the end of each period and before the balloon payment at time N, and you are paying this much per period then. I'm putting the word paying in quotes because LI is the only amount you actually pay to the lender. This amount is how much you should invest in your sinking fund each period to end up with L at the end. Take the loan amount that you need at the end, the future value, divided by the future value of an annuity immediate with end payments of 1. That'll be how much you should invest each period to get it to grow to L by time N. You're also making, again, these payments to the lender at the end of each period. You can factor out the L. This is a quantity, an expression, a formula for how much you are paying, how much money you need each payment period for this method. It turns out in the sinking fund situation, it's best to consider the outstanding balance to be your net debt. The debt of L to the lender, which you are going to owe for all the periods, minus the accumulated value of the sinking fund, so you could write it like this. That's your loan amount. This is your individual deposits into your sinking fund. We're going up to time T here, so I have to multiply that by the future value of payments of 1 up through time T. Principal repaid can then be thought of as the difference of successive net debts. So you can use this equation down here. This difference, again, this should typically be bigger than that. Your outstanding balance is going to go down typically over time. Use this formula, plug it in there, do some algebra, you can simplify it to that. Are these formulas that should be memorized? You could. Okay, I'm going to leave it up to you. I mean, they're simple enough that it's not too terrible to memorize them, especially this one. But maybe, again, you want to just be able to rederive these. These should make sense to you. And maybe not in the general case. Maybe you're just thinking about particular examples and you rederive these things. Interest paid is best, in the teeth payment, is best thought of as being the interest paid to the lender minus the interest earned in the sinking fund from time T minus 1 to time T, so you can think of it this way. Okay, this is the interest that you pay to the lender at time T. This is the interest that you earn based on interest rate J from time T minus 1 to time T. And you can do some algebra, you can factor out the L, and you can do a little simplification based on using the formula for this thing to write it this way. Probably not something you want to memorize, but hopefully something you can rederive pretty quickly. Let me end the lecture in about 5 minutes here with coming back to the continuous case. Continuous situations are not the most commonly tested things on actuarial exams, especially beyond the most basic level. But I find them more interesting, I guess you might say, so I like talking about them and thinking about them. What if you've got a continuous payment stream, in the case of constant interest rate at least? So you're paying back this loan continuously, every second of every day, every millisecond of every day. Money is going through your account and into some bank's account to pay back a loan. More likely this would be maybe a government paying a bank or a bank paying the government with some sort of continuous payment stream. Or maybe a bank paying lots of governments. Suppose you got a loan amount L that's being paid off over n periods with constant interest rate I per period and corresponding constant force of interest delta. Suppose the loan is being paid back by a continuous payment stream with rate of payment KT at time T, an amount of money per unit of time. So this is not a discrete payment amount, it's a rate of payment. You know, just pretend it's maybe $1 million per second or per month or whatever. And you're paying it every second, every millisecond of every day. And the graph of it is horizontal in the simplest case. The total payments can be found by integrating the rate of payment. I hope that makes some intuitive sense thinking about what you know from calculus. If this is a rate of payment, say in millions of dollars per month, S would be in months here, you multiply those, so to speak, and you get an amount in millions of dollars. You integrate those small amounts to get the total amount. That's the payments without taking the time value of money into account. That's a nominal amount. The present value, by taking the time value of money into account, you need to multiply these amounts by V to the S, the discount factor from time s back to time 0, these products, so to speak, would represent the present value of the tiny amount paid over the tiny interval of time ds. Imagining adding those all up by doing an integral gives you the present value of all the payments, which would be the same as the loan amount, which for the purposes of integration, you'd want to get it in terms of E and the force of interest delta. And for certain special cases, you can certainly do this integral. For example, okay, I don't have an example here, right away at least. There's some other quantities that I think are interesting to think about here. You could talk about the cumulative amount of interest that you pay from time 0 to time t. I'm calling that CIT, that's not standard notation. C standing for cumulative. How much interest do you pay over time? You have CPRt, or maybe just CPT for short, and in fact in one of the problem-solving videos I did, I just called it CPT. Cumulative principal repaid from time 0 to time t. We'll look at graphs of these things here in a minute. OBT is your outstanding balance at time t. The following equations can be rigorously derived, but should make some intuitive sense. The derivative of the cumulative interest paid from time 0 to time t should be delta times the outstanding balance. The rate of change of the interest paid, the cumulative interest paid, should be proportional to the outstanding balance. The higher your outstanding balance, the steeper the graph of CIT would be. Okay, meaning you're paying interest at a faster rate when your outstanding balance is high. When your outstanding balance gets low, down close to 0, then this derivative gets close to 0. The graph of CIT in general would be increasing and concave down because OBT is decreasing. The derivative of OBT turns out to be the derivative of CIT minus the rate at which money is going toward reducing principal. This should make intuitive sense as well, and in fact I make a few videos in my problem-solving series related to this equation and solving for OBT in various situations where KT has a certain form. This can be simplified to this. KT itself is the derivative of CIT minus OBT. That's just a matter of rearranging these equations. CPR plus OBT is constant. As your balance goes down, your principal repaid goes up by the amount needed to make the function constant there. You can differentiate both sides of that equation and rearrange to solve for the derivative of CPRt, for example, to equal this. It's the opposite of the derivative of OBT. That's kind of fast to try to understand these. They'll make more sense if we look at some graphs. We're almost done here, hang on. Graphs of these functions in the case of a constant rate of payment. And I'm labeling these graphs antiderivatives and these graphs derivatives. First look at this green graph that's horizontal. By the way, I believe this was on a loan of maybe $100,000 over 30 years, 360 months. So you can see we're going out to 360 here with an interest rate in the ballpark of, I don't know, 5% or something. KT is your constant total level rate of payment in the typical simple case. So this is the graph of KT here. This green graph is the graph of its antiderivative. It's a constant function down here, so its antiderivative is a linear increasing function. This is a positive value up here. That goes up higher. The loan amount, by the way, is $100,000. So this dashed line is at the loan amount of $100,000. You're paying total, the integral of KT, which you might call CKT, is ultimately higher than the loan amount. What else do we see here? This blue graph is OBT. It's your outstanding balance as a function of time. It's decreasing and concave down in the typical case. And this blue graph down here is its derivative, which is always negative, you see. This red graph is the derivative of CPRt. It's the opposite of the derivative of OBT. You can see these graphs reflect across the horizontal axis from each other. Notice that by the end, CPRt has to be up to this green level, the rate at which money is going toward reducing principal. At the very end, it all goes toward principal and none toward interest. This graph is the graph of the derivative of CIT, the rate of change of the cumulative amount that goes toward interest, which you see here. You can see here with this particular loan, by the end, this purple graph is above the loan amount. You're paying more toward interest overall than you paid toward the principal. This red graph is the integral of this red graph. This would be CPRt, and it has a value at time 360. It's supposed to go to time 360 there, yeah. Equal to the loan amount. Okay? I know that went by fast. It takes a lot of thinking to really get that. But I hope that is something you can get with another half hour of thinking or so and would be of interest to you. And that is the end of this lecture. Thank you for hanging